Now we're going to talk about expected values of jointly distributed random variables. And we're going to start off by looking at this theorem or proposition, which is the bivariate version of Lotus, the law of the unconscious statistician. And this proposition says that if x and y are jointly distributed random variables, either with PMF P of xy or PDF f of xy, then the expected value of a function of those two random variables, h of xy, is denoted E, the expected value of h of xy, or mu for mean. The mean or expected value are the same thing. Mu of h of xy is given by, so E of h of xy is either, if we are talking about the discrete case, either the sum over the entire support over all x and y values of h of xy times the PMF. Or if we are in the continuous case, then it is the integral, the double integral over the entire support. So here we have over the entire plane of h of xy times the density function dx dy. So it is the complete analog of the single variable case, and this theorem also generalizes to n variables, x1 through xn. So you have either a joint PMF or a joint PDF, and the function h becomes h of x1 through xn, and then you either need n summations or n integrals, depending on whether you're in the discrete or continuous case. So let's go and look at an example here. Let's let x and y have joint density function given as written here. So f of xy is 24xy. On this region here, which is 0 is less than or equal to x is less than or equal to 1, 0 less than or equal to y less than or equal to 1, and x plus y is less than or equal to 1. That turns out to be this triangle right here, and 0 elsewhere. So we are being asked first to find the expected value of x. So using the theorem above, using the bivariate Lotus, then we are taking h of xy as just x. So the expected value of x is the integral over the support of h of x times the density dy dx. Well, then we can just multiply these two functions together and integrate. And so we're going to get 24x squared, and the antiderivative of y is already done with the bounds from 0 to 1 minus x, and you just crunch through. You crunch through the calculation, expand the integral and antiderivative, and we end up with this expected value here, this expected value of 2/5. So you might think, well, E of x sounds like something that you could do in a single variable case, right? This is just a single variable, and if I did not know that y was out here, that these guys were jointly distributed, what would I do? Well, what if I use the single variable version of Lotus? Would that have been consistent? And the answer is yes. Yes, it would. The bivariate formula for the expected value is indeed consistent with the univariate formula. And so let's just have a quick look as to why that is. So E of x, remember, we're thinking that we're having this function h of xy as just being equal to x. So the expected value of the expected value of x is the double integral over the entire support of h, so x times the joint density function dy dx. But here, if we take this one step at a time, if we do the inner integral first, which I've written here in red. So if I do that inner integral, then that x value is a constant, and that can just come outside. So we have x times the inner integral, and that inner integral right, is over all y values, so we are integrating out the y, which is exactly the definition of the marginal distribution. And so that inner integral gives us f sub x of x. The x stays on the outside, and then we have the integral from minus infinity to infinity of x times f sub x of x, which is exactly the single variable definition. So that is absolutely consistent, because the first step here is to integrate out y, which means that you are obtaining something in your second step, which is exactly the single variable case. So let's go ahead and also calculate the expected value of x to the n. So now we're thinking that we have a function h of xy is x to the n, which is called the nth moment of x. And so that is a little foreshadowing of a later unit that we are going to do on moment generating functions. We are going to use this important expected value here, e of x to the n. And so what do we do? Exactly the same thing. X to the n times the density. We go through, and I'll let you look at those details, but they are the exact details that we did before, except with a new power, of x, and we end up by getting this value here as the nth moment. So whenever n value we put in, if we put in n equals 1, and you should check this, if you put in n equals 1, then you have e of x, and that we calculated before. Is 2/5. So try it right now. Plug in n equals 1, and you should see that you get the same value here. So let us go to part C. Part C, we are going to calculate now the variance and the standard deviation of x. And we're going to remember this formula from your single variable case, that the variance is expected value of x squared minus the expected value of x all squared. Well, that's kind of handy because we already have this one from a previous question, and this is, well, that's just the nth moment where n is equal to 2. So we can plug n equals 2 into that formula up there, and we'll get e of x squared. Here is e of x squared, and you go through and you calculate the answer, and you will get 1 over 25. That is the variance. The standard deviation is the square root of the variance, and so the square root of 1 over 25 is 1 over 5. There is no reason, right? This is supposed to be a function h of xy. There is no reason to limit it to functions of x. So x times y is a function of x and y, and the same thing here. So the expected value of x times y is, well, x times y times the density. It's the same thing over and over and over again. Of course, the details change. The details change of the integral depending on what you plug in right here. Right, so we have a little bit more of a complicated integral. We've got 2 little higher powers than we had before, but that is not a challenge to our algebraic skills. We just go ahead and do the antidifferentiation, do the expansion, and we will end up by getting a answer just like we did before, but this time we are looking for the expected value of a true function of 2 variables. So going ahead, the properties of the expected value, the expectation has some useful properties that can shorten your calculations rather than integrating absolutely everything. Some shortcuts can be taken, and the first three of these are completely analogous to what you should have seen in your previous probability course, and that is the expected value of a constant is a constant. Okay, it's just some constant here. And these can be proven. These can be proven either using the properties of your sigmas, if you're doing double sums, or of your integrals, right? Of your integrals, either one of those, depending if you're in the discrete or in the continuous case. The properties of those are enough to prove the properties of these expected values. So we won't do that here. We'll prove the fourth one when we get down to there, which is something a little bit new, but these first three are completely analogous to what you've seen before. Numbers 2 and 3. 2 and 3 put together are often called linearity, the linearity of the expected value. Number 2 says if you have a constant times the function, well, you can pull that constant outside, right? Again, it is just the properties of the sigma of the integral. You can pull constants out of those, so it should come as no great surprise that you can pull constants out of the expected value. And the same thing for number 3. You can split sums and integrals over pluses and minuses. So in fact, this really should say plus or minus here, plus or minus. Minus is just adding a negative anyway. They are really the same thing. So it should come as no great surprise. Great expectations was going through my head. Very strange that. So no great surprise that you can split up the expected value over a plus or a minus. So the expected value of h of x y plus or minus g of x y is the sum or difference of the two expected values. So what is new? What is new then is number 4, and that is the following, that if x and y are independent, so we have seen that previously, if they are independent random variables, then the expected value of a function of x times a function of y is the expected value of the function of x times the expected value of the function of y. That is something which is new because we are using two different variables here, and those variables are independent. So let's go ahead and prove this and see why this is true. So if we have the expected value of g of x times h of y using the bivariate lotus, that is g of x h of y times the density function, and here is where independence comes into play. The independence, you remember that two variables are independent if and only if their joint density function is the product of their marginal density functions for all x and y. So that is what we are using. That is what we are using right here to split that joint density into the two marginals, the product of the two marginals. Well, now if we can do that, well, we can group together the x's and group together the y's, and guess what? In terms of the inner integral, the first set, the x's are constants, and so we can pull those out. And then obviously we can do the second step, pull out the constant with respect to y, and we have this property that we have seen before of double integrals. If what you have is over a rectangle, so this is a massive rectangle, it's the entire plane, right? So there's maybe a little justification to be done there, but that is true here. So if we have these factors, if the integrand factors over a rectangle, then you can factor the integral, the double integral, as a product of a single integral with respect to x and a single integral with respect to y, and those are the definitions. Those are the definitions of the expected value of g of x and the expected value of h of y. So there is our fourth property, which is a useful property, but only to be applied when you know that the two random variables are independent. So let's look here at one last example. Let's let x and y be independent random variables with respective density functions. So here's the density function of x. So 1/5 e to the minus 1/5 x for x is greater than 0 or 0 otherwise. And the density for y is 1/4 e to the minus 1/4 y. Y is greater than 0 or 0 otherwise. If we let t be this expression of x and y, we are asked to find the expected value of t. So we're going to go ahead and do this. This is going to be an application of the properties, but also an application of your memory, because both of the x and y density functions are of this form, and that is the form of an exponential random variable. So x and y are both exponential random variables. They have different lambdas. The lambda for x is 1/5. The lambda for y is 1/4. And then we have to remember little values, little theorems that you had in your previous course. The expected value of an exponential random variable is 1 over lambda. The variance of a exponential random variable is 1 over lambda squared. So if we calculate both of those, for x and for y, we get the expected value of x is 5, expected value of y is 4, and 25 and 16 for their respective variances. So that is ingredients that we are about to use because we want to calculate the expected value of t, which is going to be the expected value of, here's the expression for t. So we want to use the properties of the expected value. So we are going to expand. We are going to expand this square, and then we are going to use the linearity of the expected value to bring out the constants and split the expected value over the sums and differences with this property here that the expected value of a constant is a constant. So we have to evaluate this here, the expected value of x squared. The expected value of x squared, well, that gives me this. How does that give me this? Well, there's a little note down below. V of x, we know, is the expected value of x squared minus the expected value of x all squared. If I want this, I can push this guy over to the other side. And so e of x squared is v of x plus e of x squared. That is what has gone right here. The same thing I've done for e of y squared. I'm using the same property here. What I'm using here, e of xy is e of x times e of y. That is not always true. That is only true because we are told that those variables are independent. So the expected value of their product is the product of their expected values. Now that we've used all those properties, we have these values from above and from this value here is already given to us, so we just plug them in and calculate, and the expected value of our random variable t is 220. So much easier to use our memory of the expected value and the variance of the exponential random variable and the properties of the expected value to calculate this. Much quicker to do that than to integrate. If we'd wanted to integrate, we would have had to first come up with a joint density function, which is not difficult to do because these values are independent, and we would have had to do the double integral over the entire support of this t value, t of xy dx dy, and that is a much longer thing to do than what we just did.